All right, so for the second part, I'm going to prove to you a theorem that talks purely about the topology of R, but follows easily from things that we already did. This is why all of these theorems have different perspectives in a way they're talking about different things. So the theorem, I think some people attribute this to Cantor. I'm not really sure. It's called the nested set theorem or nested compact set theorem. Right? And the statement is as follows. Let F be a family, compact sets. Actually, I need to sort them, right? Let me use the same letter as the textbook. By the way, the textbook doesn't prove this the same way I did, just in case you're following Royden's book, or similarly the other one. This proof, the one I give, is a little shorter, but it's just because of the way I wrote it. Okay, sorry, it's not an A, it's an F, right? So we have a sequence of sets. It's a family of compact sets that are ordered in a descending order, right? So the biggest one is F1, and they're getting smaller and smaller and smaller. Right? It's a countable family. And then I claim that if you intersect all of them, now the intersection, of course, might not be a set of the same type. It might not be an element of the family. It's not necessarily the smallest of them. But the only thing I'm going to claim is that it's not empty. And there's other conditions that people add to this theorem in which they say if the diameter is decreasing and the limit of the diameters goes to 0, then this is not just non-empty, but it's actually exactly 1 point. That is not difficult to prove from what we're going to do, but we have to leave something for real analysis. So let's just focus on this one statement, which is the deeper and the harder part, and the one that I find more interesting and useful. Okay, so does the statement make sense, or are there any questions about this? I think I need to ask something else. I need to say that all of these are non-empty, right? Because like I said, the empty set is compact. So if this family is eventually everything is empty, then obviously the conclusion will not be true. So yeah, I have to ask these to be non-empty. Actually, what I wrote is correct, but maybe it's better if I just say of non-empty. To avoid confusion, right? I'm not saying that the empty set is in the family or something. Okay, so let's prove this, and you'll see the proof is very simple with the things we already did. And how do we do this? Let's actually, before I write down the formal proof, what is the intuition behind this fact? The intuition is as follows. If you have a compact set and you split this into smaller but still compact sets, then the idea is that no matter how you go about doing this forever, you cannot avoid always keeping something inside all of these sets at the same time, right? And it's not just that you're splitting them, it's basically that as you shrink something, as long as every piece is still compact, there will always be something that is in every single one of them. I think there are some exercises either in the tutorial or the extra problem sets that I devised for you, in which you have to come up with what happens if these are not compact, meaning both closed and bounded. And in that case, of course, everything breaks down and it doesn't work anymore. You do need both properties, and you need all of these sets to have both properties at the same time. Even though the proof will only require the biggest one to be compact, all of them are compact, of course, right? Okay, so let's write down the proof. So by contradiction or contrapositive, suppose not. Suppose that the conclusion is false, meaning that this intersection is empty. Now we're going to use something that wasn't, I think, named in the foundations chapter, but you've definitely heard about this, the Morgan's laws. De Morgan basically says the complement of the intersection is the union of the complements, right? And in reverse. So how do we use this? Since, and let me do it this way. Allow me to write it this way. So we have Fn, the intersection of all of these. I should, of course, put the indices, otherwise. If this is empty, then I can just take the complement on both sides. The complement of the empty set is R, and the complement of this is, I don't know, but it's that, right? Now, by De Morgan's laws, I know that the complement of the intersection is the union of the complements. And if you need me to elaborate on that, I'd be happy to. Because like I said, we didn't call this De Morgan's laws, but this is something you would have definitely seen somewhere else with that name. Okay, so is this step clear, what I did? All I did was flip the complement inside, right? Now there is something worth noting. These are the complements of closed sets. So if you've done your homework, then you should know that these are open sets. The complements of closed sets are open sets. And what does this tell you? Well, the real numbers, of course, contain everything. In particular, they contain F1. So this union that I underlined in blue is an open cover of F1. So the complements, complements, actually, I'm starting with 1, right? Is an open cover. And now I could do this with I could do this with F17, right? It doesn't need to be F1. But I don't know. Let's do this with F1, which is compact by compactness. Like I said, I could have done this with any one of these, because they're all compact. Take how should I write this? F1, actually that's, oh boy. Let's just use the notation of a subsequence, right? So this is Fn1, Fn2, all the way to Fnk, right? So take all of these such that F1 is still being covered by the complements of these, right? So from 1 to k, this is R minus Fni. If that makes sense. Okay, so F1 is covered by this weird set that I have here, so just extract a finite subcover of it by compactness, and I'm doing this. Now notice that, of course, I wrote the theorem with the word compact, but if I change the word compact to closed and only the first one of them bounded, because then everything is bounded, the conclusion still holds. So I am implicitly using the Heine-Borel theorem that I proved earlier for this to be useful, right? Because like I think I showed you that using the definition to show that something is compact isn't really nice, right? It's a bit cumbersome. So we do need this theory for this to be useful. Okay, so now we have that open cover, and what do we do now? Why is it important that this is a finite union? So any ideas how I would conclude from here? Any questions from the proof, or does it make sense until now, more or less? So what do we do? There's one hypothesis that we haven't really used. And now that I think about this, there was a slightly easier way of writing this. I mean, it's fine. It's fine. Let me change the indices just so that it's easier to write. There's nothing wrong with what is written now, but there's an easier way of writing this. And let me explain this, and this will hopefully make sense. So this sequence right here is a finite subsequence of the original set, or the original family, right? I'm only taking a few of them. But what am I using these for? I'm using these to cover a set. Now, I only care about this cover being finite. I don't really have any control. I cannot restrict and say I only need 10 of them or 100 of them. It could be millions of them, right? I don't have any control over that. So why do I bother writing it like this? I could just say, well, if the biggest index here is 1000, then just take the first 1000, right? If it's too many, it doesn't matter because I only care about this being finite. So let me change this a little bit. Or should I change it? I mean, it's fine the way it's written now. Maybe it doesn't matter. Okay, so let's just say, yeah, let's not change it. This will only be more confusing. So let's say that I pick these indices in order, right? And then what can I say about this? F and K is the smallest of all of these sets because this family is shrinking, right? Let me make a sketch for you. Cannot move this. Okay, there we go. So this family is shrinking. So I have here F1 and smaller is F2, right? And if I'm picking a subsequence of this, eventually I will hit whatever this big number F and K was. So this F and K happens to be contained in all of the other ones because this family gets smaller and smaller. That's written in the hypothesis of the theorem at the very beginning, right at the top. So what does this tell you? What does it mean that F is contained in the complement of all of these? F1, and by extension, everything else, right? So where is the contradiction here? F and K is contained in F and 1, F and 2, all the way up to F and K, including itself, right? It's contained in all of them. That means that if you take the complements, F and 1, the complements are F and K, are all contained in the smallest one, whose complement would of course be the largest one, right? When you take complements, it flips. Does this make sense? Why is this problematic? Who can tell me why this is problematic? Therefore, Fn, which is contained in the union of all of these, well, that one must be contained in this other set, right? F and K. Do you see the problem with this? Where did we derive the contradiction? Basically, the problem is that when we have a finite cover with this property, since these are shrinking, it means that I can find one that is contained in all of them. But that can never happen because then when I take it away, what I get is empty. And each one of these is empty. Sorry, non-empty. Each one of these is a non-empty set. So let me highlight this for you. Does that make sense? Let me maybe pause here for a minute or two. So for the last result that I want to mention, I just want to connect these ideas with sequences. Because remember, if you recall what we did last week, everything that we've talked about closed sets has been almost purely topological. But closed sets can also be defined in terms of sequences. A set is closed if every sequence that converges inside the same set, right? So basically, a closed set is one that contains all its limit points. If you find a sequence that converges outside of the set, well, then your set wasn't closed, right? Now, how does this translate to compactness? Because compactness is stronger than being closed. Compact sets are not just closed, they are more. So surely there's a way to talk about compactness just in terms of sequences. So how do sequences play a role? Play a role. And that is the last question that I want to answer about this, and then we'll have some time to talk about the quiz that I prepared for today, as well as some general questions, general insights about why this matters. So a very brief definition that you may have heard about before, a sequence of real numbers. Remember, it's just an enumeration of some real numbers, right? That's what a sequence is. Okay, so let a sequence S and take an injective function. An injective function, let's call it I, although it doesn't matter. It's a re-indexing of the natural numbers, right? Then let's see if this makes sense. S composed with I is called a subsequence of S. Right, so every time you have S and you compose it with something injective, you get a subsequence. Now, this might be a bit more formal than we need. If x0, x1, x2, x3 is a sequence, then a subsequence what could be a subsequence? Well, you just have to take some of these natural numbers, right? Some injective. Injective means that they don't repeat each other. You cannot have x0 then x0 again. That's not allowed because that wouldn't be injective. But a subsequence could be, for example, you just take the even indices, right? This would be the injective function 2n. N sent to 2n, 2 times n, right? 6. This is a subsequence. Another subsequence could be 0, 1, and I don't know, then you skip a bunch of them, and then you just continue afterwards, right? Or just the prime numbers, and so on. So a subsequence is basically you take some of the elements of the sequence, forming another also infinite sequence in the same order and with no repetitions, and you're not allowed to change them or to change the order or anything like that. That's what a subsequence is. Something that you will learn, and this is something that I don't want to prove, even though the proof is not complicated, and that is that all subsequences, how do you write sub? Of a convergent sequence. This is very easy to prove. Very, very easy to prove. And oh, okay. I just have a question in the chat. You're right. It's not enough for it to be injective. If I want this not to change the order. Thank you. Thank you. This is very good. Strictly increasing, of course. Injective would mean that I'm allowed to do x0, x4, and then x2, and then x6. And no, no, no. Strictly increasing. Thank you. Yes. No, don't change the order. That's a really good observation. All subsequences of a convergent sequence also converge to the same point. And this is really easy. You need nothing other than the definition of convergence, right? Because the fact that these are strictly increasing, and of course that you cannot change the order, tells you that you may need to wait a little longer, but eventually the definition of convergence is also verified for these. And if you try to make a sketch, then this is clear, right? You have a point, and you know that this is the limit of some sequence. If you remove elements of the sequence, but the sequence remains infinite, well, it has to converge to the same point, right? You couldn't possibly avoid this. Um, if you just want to build up some intuition, then I can ask you a question that you should be able to answer fairly quickly. Is the converse true? Unless this is the first time you're seeing sequences and convergence in this course, then I think you shouldn't have any problem answering this, right? Is it true that if a sequence has a convergent subsequence, actually, wait, let me, I have to rephrase this in a slightly more concrete way. So it's not exactly the converse what I mean, right? So if a sequence does not converge, can subsequences. It is the converse in the sense that, okay, I'm getting answered in the chat. Okay, yeah, like I said, this isn't too hard to answer. So the sequence 0, 1, 0, 1, 0, 1 alternating is not convergent because it doesn't approach anything, right? You just have to circle around any point and eventually it keeps skipping, jumping between 0 and 1. But the sequence of odd numbers, which is just the zeros, or the other one, which is just ones, those one converge because they're constant, right? Of course, they converge to different points. I'm pretty sure you can prove something like that. If you have a sequence that doesn't converge, maybe you need to add some assumptions to that. Then you should be able to find subsequences, assuming it's bounded, subsequences that converge to different points or something. But anyway, that is enough to answer this question. So thank you. Okay, so here's something interesting, and this is a theorem that I don't know. Maybe it's a lemma. Bounded sequences always have. So the question is, what types of sequences have convergent subsequences? Well, if the sequence itself converges, I already told you, yeah, of course, everything converges. But what if it doesn't? Can we still say something? So bounded sequences have convergent subsequences. If we have time, which is unlikely, but we can see, there is a way to prove this fact that I just wrote down using purely combinatorial techniques, which is counterintuitive because we haven't mentioned anything about combinatorics in this chapter. So you can prove this using just things about not really enumeration, you know a little bit more than that. But this has nothing to do with, you can prove this in a much more elementary way, is what I'm trying to say. Let's prove this. And just in case you're tired of me writing so many long and technical proofs, let's do this as a sketch. Let's do this as a sketch. And how does this even work? So the way this is going to work is that we are trying to hunt a lion. In fact, I have a lion plushie right here. I know you can see it. My camera sometimes doesn't work. Okay, can you see it? I have a lion plushie. Okay. Anyway, in the savannah or wherever lions live, people used to hunt lions by restricting their territory, either using probably not fences, but something more like fire or some other sort of artificial man-made barrier, and enclose the area. Thanks. enclosed the area more and more until the lion was trapped and had nowhere else to go. Because, of course, lions are much faster than humans, at least for short distances. I mean, I think I don't need to explain that in too much detail. So the idea is that we're trying to hunt down a lion. And this is actually pretty beautiful if you think about this from a very intuitive perspective. So if you have a sequence of points, so let's imagine this in R2. Of course, we usually write these proofs in R because it's simpler, but imagine this in R2, I feel like this is useful. So there must be a ball that contains everything because that's what bounded means. It means that everything happens inside some ball. Obviously, an unbounded sequence might not have any convergent subsequences, right? For example, if you take the natural numbers as a sequence, 0, 1, 2, 3, 4, 5, that is unbounded, and it doesn't have any convergent subsequences because all subsequences eventually go to infinity, right? So we this is not true at all. Actually, can I? Yeah, of course, of course. If it is unbounded, this is an if and only if is what I'm trying to say. So if this is bounded, we have a sequence. And what this theorem is telling us is that no matter how you try to order and cluster these points, they will always accumulate somewhere so that they converge. So that eventually the whole sequence, a subsequence converges to that point. And this is like an interesting game if you think about it. Because picture it this way. You're trying to select infinitely many points inside this set, right? But you want to keep them from clustering. You want nothing to converge. So how would you go about doing that? Well, let's pick the first point to be x0, someplace here. Now, let's pick x1 to be something really far away to make sure that they don't cluster. And then x2 must be something also far away so that they don't cluster. So this is like the lion that we're chasing, right? And as we're enclosing the area on the lion, eventually this lion will be like repeating many, many points. And just because it is forced to move indefinitely, it will have to repeat the same area over and over and over again. So as I keep adding points, and I can do this in any order that I want, doesn't it seem interesting that eventually these points are forced to cluster? They are forced to cluster together. Now, I'm not saying that the sequence itself will converge. I could keep jumping between x0, x1, x2, and then repeat those 3 points. Of course, that will never converge. But if I keep adding points forever and ever and ever and ever, eventually you'll be able to circle in on some cluster of points and identify a sequence, a subsequence that does indeed converge and will always contain infinitely many points. So I find this quite interesting. And if you're interested in this in a much more general setting that you will not cover in real analysis, you can look at ergodic theory or dynamical systems, and they have a lot of results that have this flavor, but taken to the next level. Okay, so how does this proof work in an intuitive way? So the idea is that we need to enclose this area into smaller and smaller pieces, right? So how do we capture a lion? First thing you do is whatever region the lion moves in, whatever area of land that he dwells in, you cut it in two pieces. Now you know that eventually one of the two pieces will always have infinitely many points, meaning the lion will be mostly in one of these two pieces, right? Because even if the lion alternates between these two slices, the points, okay, I guess the analogy starts to break down when you talk about infinite points, but you keep dividing this into smaller and smaller pieces. And then what we want to do is we always select one of these pieces with infinitely many points, right? So for example, maybe here the left side has infinitely many points. The lion will be forced to visit that point infinitely many times. If you think about it, this is sort of the pigeonhole principle, right? We haven't talked about this. That's the topic for the next chapter. But if the lion only visited each half finitely many times, that means that the lion visited a total of finitely many points because there are just two halves, right? But that is not true. Sequences are infinite. They're allowed to repeat infinitely. They are allowed to repeat the same point many times, but they cannot. They can never stop. So you keep doing this, and you always pick the half that contains infinitely many points. It might not be unique, right? Maybe both halves have infinitely many points. And as you enclose and enclose and enclose, eventually you will force the lion to be trapped. So this is like hunting a lion, right? So the trick is use the nested, and you can make these sets closed, right? Because why not? Just divide them and take the closure. Nested closed sets. Since this is bounded, these will all be compact. Use nested closed sets and apply the theorem. The theorem that talks about nested closed sets tells you that there's a point in the intersection, right? So there is a point, call it L for lion. There is a point that is in the intersection of all of these pieces, right? So this is L. Oh. And then you just have to prove that by the way that you chose this, namely that every single piece that you're picking has infinitely many points, it should be very easy for you to show that L is the limit of this sequence, right? Just pick one point. You don't need infinitely many. So the first time that we picked this slice, we said left. There's infinitely here. Then the next time we said this set, and then this set, and then this set, right? And as you pick them, they get closer and closer and closer, and that's how you would find the subsequence. So let's call this n0. This one is xn1, xn2, xn3. You can do this because you always pick the one that has infinitely many points. So just pick one of these points for each set, and that's all you need, right? By the way that you chose these, if you pick them the right way, L is the limit, right? So as you can see, this isn't too difficult, and I should have given credit. I believe this is the one that's called Bolzano-Weierstrass. Some people might disagree what these theorems are named because historically these theorems contained not just one but multiple results, intermediate results, and some people consider other results deeper, and that's the one that should be called after the name, you know? So this is Bolzano-Weierstrass. And as you see, we are using the nested closed theorem that I just proved to you. Now there's something else that I find interesting. I just convinced you in a very sketchy way that bounded sequences always have convergent subsequences. That means that a sequence inside a bounded set must have a convergent subsequence because a sequence inside a bounded set, well, is itself bounded by the same bound, indeed, right? What about compact sets? So a bounded, not bounded, a sequence. Sorry, not bounded. A sequence inside a compact set. Well, compact means that in particular it is bounded. So this sequence will have a convergent subsequence. But that's not really the only thing I care about. Compact sets, by the thing I just proved, compact sets are also closed. So if I have a sequence inside this closed set that converges, the limit point must also be inside the closed set. So let me write this a little bit more precisely because you will actually need these ideas for the quiz so that this isn't as sketchy. So let K in R be compact. Same thing works for Rn, but the quiz is written in R, so let's just say R. Let K be compact. And Xn sequence of real numbers inside K. Then the limit exists not the limit. Then there is subsequence, and let's just denote it with K, no, not K, with L, right? Such that the limit of these things is inside E. This is what we call a convergent subsequence. It's not just a subsequence that converges, but it converges, inside K, right? And this is what I would call the Bolzano-Weierstrass theorem, but maybe it's not that important. Now that I think about it, there's something better that I can do. And K. Okay. Sorry about this. Let me edit this because I like to always give the stronger version of this. Just change the way this is written. Okay, so let K be a set and a sequence inside. No, that's not what I want to write either. Sorry about that. Okay, sorry. Let K be a set. Then K is compact if and only if every sequence contains a convergent subsequence. So it's an if and only if. It's not just one direction. And one of these directions is, if I'm not mistaken, part of your quiz. Let me quickly check which one it was. Or in fact, if someone has it there, would you mind telling me which of the two directions is part of the quiz? So I do the other one. Okay, I got several answers. In the real numbers, if a set E is such that every sequence has a convergent subsequence inside E, then E is compact. Okay, thank you. Thank you to all of you that answered this. Right. So let's do the proof, and I will maybe skip some details so that you have something to write in the quiz. Okay. So the forward direction is that if something is compact, then every sequence has a convergent subsequence. Let's do the forward proof, right? Okay, so suppose this is not part of the quiz. Suppose K is compact, because that's what the forward direction says. And okay, it's compact. Then, by the Heine-Borel theorem, compact means something weird about covers, and we could use the definition to prove this. There is a way to prove it. It's a bit longer. So by the Heine-Borel theorem, say this by Heine-Borel, K is bounded. Then using the Bolzano-Weierstrass theorem, and what happened? Using the Bolzano-Weierstrass theorem, it's bounded, so the sequence has a convergent subsequence. But the limit might not be inside K. However, it will be inside K because K is not just bounded, but also closed. So we do need those two properties. Now, I do need to tell you how to do the other direction, but my pen is acting up like it sometimes does. Give me 1 second, and in the meantime, let me know if there are any questions. No, there's no way to fix it when it's already acting up. Okay, well, this is unfortunate. Okay, let me pause the recording.